Welcome to MCV for You, Unit 1, Intro to Calculus. Today we will begin looking at reviewing and rationalizing the denominator. First, we will begin looking at the slope of the line. When given 2 points, such as x1, y1, and x2, y2, recall, to find the slope of a line, we take m equals y2 minus y1 all over x2 minus x1. When finding the equation of the line, remember the equation of the line is equal to y equals mx plus b. Recall that b is our y-intercept, and m from above is our slope. So we will begin looking at our first example here, where we determine the equation of the line. We have our slope to be 3, therefore m is equal to 3, and our y-intercept to be negative 2, therefore our b value is equal to negative 2. Using our above equation, y equals mx plus b, we can sub those two values in to have y equals 3x minus 2. And this is your final answer and your equation of the line. For the next example, we are given 2 points, negative 3, 1 and negative 5, 7. Remember, a point is always in the form of x, y. Therefore, we will take the first point as x1, y1 and our second point as x2, y2. Our first thing that we need to do is we need to find the slope. So we are going to take those values and sub it into our slope formula of m equals y2, so 7 minus y1, which is 1, all over negative 5, since that is our x2 value, minus negative 3. We then can add and subtract our numerator and denominator. So our numerator is 7 minus 1, which gives 6, all over, in our denominator, negative 5 minus negative 3. Recall that this will change this to negative 5 plus 3, because two negatives make a positive. Therefore, we have negative 2. 6 divided by negative 2 is equal to negative 3. Now that we know our slope value, which is our m, we are going to use that in one of our points, it doesn't matter which point, to sub in to our equation y equals mx plus b to solve for our b value. So we will use our first point here, so we have 1 is equal to negative 3 times negative 3 plus b. Therefore, this is equal to 1 equals negative 3 times negative 3 is positive 9 plus b. We will then bring that negative 9 over to the left side. Remember, when you bring that negative 9 to the left side, anytime you cross the equal sign, our sign changes. So now we have 1 minus 9 is equal to b. 1 minus 9 is equal to negative 8, which gives us our b value. And our third step is to sub that into our slope of a line. So we have y equals negative 3x minus 8. And that is our final equation. In part C, a graph is shown with 4 different lines. So looking at these 4 different lines, we're just going to discuss the values of our slope and our y-intercept. When given a visual, what you always want to look at is where your values hit your y-axis for your y-intercept value, and then you can take 2 points on the graph and find your slope. Or you easily could do your rise over run. So for our part A here, which is our horizontal line, so A, when looking at this, you notice any horizontal line will not have a slope. Therefore, it's only going to have a B value, a y-intercept value. So you can see there that your y-intercept value is 3. So for any value of x, your y is always going to be 3. So your form is just y equals 3. For part B here, or slope B, line B, we have a slope, but you notice it is going down from your left to right. Therefore, I know I'm going to be dealing with a negative slope. So if I look at 2 points, say our point right there, which is at 3 and 0, and our other point, which is at 1, 1, we can use those 2 points to find our slope. Since this is a pretty small graph, looking at this, I notice now I did part A wrong, and that should be y equals 2. Sorry about that. So your B, we can visually see that our slope, if we look at our rise, which is going to be negative, if you go down 1, 2, and over 1, we get to the other point. So therefore, down 2, so that'd be negative 2 over positive 1, giving us a slope of negative 2. Also, notice that your B value, which is your y-intercept, is equal to 3. Therefore, y is equal to negative 2x plus 3. Now go ahead and try doing C and D. Now we will discuss the domain and range. The domain is a set of independent values which is x, for which the function is defined. Where the range is a set of dependent values, y, for which the function is defined. Example 2, we want to determine the domain and range for each. So we will begin by looking at our semicircle, our oval. We want to look at what x values for our domain exist and what y values for our range exist. When we are given a shape like this, you'll notice that we will have values that are in between two x values and values that are in between our two y values. So our first one here, our domain is equal to the x as the element of the real numbers, such that you can see here that our value is at negative 3 to positive 3. And it also includes those values. So we are going to say negative 3 is less than or equal to x, which is less than or equal to 3. Where our range is going to be, we set it up the same, y is an element of the real numbers, such that we have our values here, which are 1.5 and negative 1.5. We can also write that as a fraction, but I'm going to write it as a decimal for now. So negative 1.5 is less than or equal to y, which is less than or equal to 1.5. Another way we can write this is using brackets to show our interval. These square brackets mean that the values are included. If I used round brackets, it would just mean that it was less than. And for our y value, we also can use our square brackets. When we are looking at part B here, you'll notice that our value for our x starts at negative 2. It will be no other value less than negative 2 for this. So therefore, we can write our domain as x is an element of the real numbers, such that x is going to have to be greater than or equal to 2. And you'll notice for our range that this function will never be negative. Therefore, y is an element of the real numbers such that y is greater than or equal to 0. Again, we can rewrite this using 2 to infinity. Anytime we're writing it with infinity, we're going to use a round bracket since we don't know what infinity is, as well as our range 0 to infinity. But notice we use the square brackets around the 2 and the 0. Example 3. A function f is defined by f at x equals x minus 1 squared minus 1 for x is greater than or equal to 1, and 2x minus 1 for x is less than 1. We want to sketch the function and then find each a, b, and c. So we'll begin by first sketching our x minus 1 squared minus 2. Recall that this is a quadratic function, however, we're only going to sketch the parts where x is greater than or equal to 1. So we can begin by first looking at when x is equal to positive 1, y is equal to negative 2. We then know by looking at this that this is in our vertex form, and therefore our 1, negative 2 is actually our vertex. So we can then use our step pattern to be able to graph the other parts of this function. So recall that our step pattern is over 1, up 1. Over 1, up 3, and so on and so forth. We can connect these, always including an arrow at the end, of course, and then we can graph 2x minus 1 where x is less than 1. So when we have x is 1, we're going to start at that value, and therefore our y value would be positive 1. Remember, we can just find that by subbing into this 2x minus 1 equation. Or, since this is a linear function, where it's 2x minus 1, we could use the fact of we know the slope and we know what the y-intercept is. So when we're graphing a linear function, you can always start with the the y-intercept, and then use our slope up 2 over 1. And this is where our x will be equal to 1. And since it does not include 1, we're going to have to open circle there to show that it isn't included. And then we can just draw our line to connect the rest. This type of function is what we call a piecewise function. We can then find each of these values. For f at 3, we know that we're going to have to use our first part of our piecewise function, which is x minus 1 squared minus 2, which is the quadratic portion. We can sub in our value of 3 for our x, and when we do that, we are going to have 3 minus 1 squared, where 3 minus 1 is 2, so 2 squared minus 2. 2 squared is 4, 4 minus 2 is going to be 2. For f at 1, since our linear part of this function, 2x minus 1, does not include positive 1, we will sub in that positive 1 into our quadratic portion. And when we sub that value in, we're going to have 1 minus 1, which is 0 squared minus 2. Therefore, f at 1 is equal to negative 2. And f at negative 2 is going to work with our linear function, since it is less than 1. So when we sub in negative 2, 2 times negative 2 will give us negative 4 minus 1, which is equal to negative 5. Next, we're going to look at rationalizing. To rationalize the denominator, you need to get all the square roots out of the denominator. So, in example 4, we need to simplify each by rationalizing the denominator. This should be review from grade 11 and advanced functions. So we will begin with a here, 3 over the square root of 3. To rationalize this, all we're going to do, I'm just going to rewrite this, we're going to multiply both the numerator by root 3 and the denominator by root 3. Since we are multiplying both the numerator and denominator by the same thing, we're not changing the function at all. Therefore, we're going to have 3 over root 3 all over. When you're multiplying two roots, you multiply the numbers underneath. So therefore, root 3 times root 3 would be equal to root 9. But because the characteristics of a root roots, when you multiply two of the same, it's actually just going to end up being 3. And therefore, we can then cancel out those 3's, and we're just left with root 3. In part B here, we're going to do the same. However, now we have a 2 in front. What we need to remember is we only need to get rid of the roots. Therefore, you're going to multiply both the numerator and denominator by root 5. Therefore, we're going to be left with 3 root 5. Remember, when you're multiplying the same roots together, it's just going to be the number that's underneath the square root sign. So in this case, 5. So we'll have 2 times 5. And 2 times 5 we all know is 10. So we're left with 3 root 5 all over 10. Part C is a little bit trickier. And what we need to do is we're going to multiply not only by the roots, but you need to multiply by the signs. If I were to just multiply this by root 2 minus 3, it's going to give me a longer function, and therefore it's not going to have the middle numbers canceled out. So we need to make sure that we multiply by the opposite sign. So we have root 2 plus root 3. And when we do this, we're going to multiply this 3 root 2 by both things. So 3 root 2 times root 2, you'll notice we have the same roots here. So that's going to actually be 3 times 2. Plus, here we will have 3 root 6, because 2 times 3. All over, we'll have 2 minus 3. So what we're going to be left with, we'll be left with a negative 1 on the bottom, because 2 minus 3. So we know our whole function is going to be negative. So that will be left with negative 6 minus 3 root 6. Now you can go ahead and try D on your own, and please continue to trying example 4. We will take that up in class tomorrow.